Okay, let's dive right into this explainer. Today, we're going to completely redefine two words you probably use every single day, but, well, you might actually misunderstand them. I'm talking about work and power. Think about it. If you've ever said you were working hard on a massive jigsaw puzzle or powering through a really thick book, physics is about to tap you on the shoulder and say you might have been doing absolutely nothing at all. Sounds crazy, right? Let's unpack it.
So, here is our roadmap for mastering these concepts. We'll start with the strict definition of work, move into calculating work done, look at some weird edge cases where forces do zero work, then we'll tackle understanding physics power, and finally, we'll see how this energy plays out in the real world. RA Section 1, the definition of work, everyday versus physics. You're going to need to leave your standard dictionary at the door for this one.
So, in our everyday lives, sitting motionless at your desk, just thinking as hard as you possibly can about a complex math problem, that feels like a ton of work, doesn't it? You get tired. But in physics, if there is no physical movement, you are doing absolutely zero work. None. Zero. It doesn't matter how much mental effort you're expending. For physicists, work exclusively happens when a force actively causes movement. Even just making the ink flow from your pen, you have to push against the force of friction on the paper. That is when you're finally doing work in the physics sense. Fundamentally, doing work is simply the act of transferring energy. No movement, no transfer, no work. Think about lifting a really heavy box. To do that, you have to apply a continuous upward force pulling against the constant, invisible downward drag of gravity. And as that box rises up, your applied force is moving upwards too. Now, you need a store of chemical energy in your muscles to actually pull this off. And what you're doing is effectively transferring your energy into the box itself. It becomes gravitational potential energy. Your force is simply the vehicle for transferring that energy. So, the amount of work you've done, it is exactly equal to the amount of energy you transferred. It's a perfect exchange.
Moving on to Section 2, calculating work done, the formula. Now that we've got the concept down, let's look at the actual mechanics of it. The absolute most crucial takeaway here is this beautifully elegant equation. Work done, which we represent with a capital W, simply equals force times distance. But, and this is a massive but, it's not just any distance. It has to be the distance moved exactly in the direction of the force. And because we know doing work is just transferring energy, this whole thing is perfectly equal to delta E, meaning the change in energy. It's super logical. A massive force moving through a massive distance? That does a lot of work. A tiny force moving a tiny distance? Very little work.
And because we are measuring this transfer of energy, we use joules. Let's look back at that formula for a second. Force times distance. We measure force in newtons and distance in meters. Put them together, and 1 joule is exactly the work done when a force of 1 newton is applied through a distance of 1 meter. Literally, 1 joule equals 1 newton meter. It's a brilliantly simple relationship. Let's actually break down a problem step by step just to build up your mental model. Whenever you face a physics problem, your first move is always to extract the data. Step 1, write down exactly what you know. In our example here, we've got a force of 200 newtons and a distance of 2.5 meters. Step 2, write down that foundational equation we just learned, work equals force times distance. Step 3, plug in the numbers and calculate. 200 times 2.5 gives us a clean 500 joules of work. Easy, right? Let's see this in a real-world scenario. Imagine a girl using a wooden plank as a ramp to push a heavy 400 newton box up onto a raised platform. She's applying a pushing force of 200 newtons over the entire 2.5 meter length of that ramp. Just like we calculated a second ago, she does 500 joules of total work. But hold on a second. The actual vertical height she lifted that box is only 0.75 meters. If we calculate the work done strictly against gravity, which is the box's weight of 400 newtons multiplied by that vertical height of 0.75 meters, we only get 300 joules. That means the box only gained 300 joules of gravitational potential energy. So where on earth did the other 200 joules go? Well, it wasn't destroyed. It was completely used up fighting friction as she dragged that box scraping up the ramp. It turned into heat. Okay, let's jump into Section 3, forces doing no work, the edge cases. We're going to look at some highly counterintuitive scenarios where you have massive forces at play, but mathematically, zero work is being done.
Picture a man sitting perfectly still in a chair, just reading a book. Now, there are very real, very strong forces acting on him at this exact moment. Gravity is pulling his mass downwards, and the chair is providing an upward contact force to stop him from plummeting through the floorboards. But because he isn't moving any distance whatsoever, the d in our equation is 0, and force times 0 is, well, it's 0. Therefore, despite gravity relentlessly pulling on him, the physics work done on him is absolutely 0. His energy isn't increasing or decreasing.
Let's scale this up to a cosmic level. Imagine a spacecraft traveling in a perfect circular orbit around the Earth. The Earth's immense, mind-boggling gravity is constantly yanking on this spacecraft, pulling it straight toward the center of the planet. But because the orbit is circular, the spacecraft never actually gets any closer to Earth. It has 0 movement in the actual direction of the gravitational pull. Instead, it moves perfectly perpendicularly to it. Because there is no distance moved in the direction of the pulling force, Earth's gravity actually does 0 work on the spacecraft. Its kinetic and potential energy just stay perfectly constant as it glides through space.
Pretty wild, right?
All right, on to section 4, understanding physics, power, time matters. It is time to introduce a completely new, totally critical variable to our understanding of the physical world. Let me throw a scenario at you. Imagine you carry a huge, heavy crate all the way up the stairs to the roof of a 20-meter building. Exhausting. Now, imagine a massive industrial construction crane lifts an identical crate to that exact same roof. Both of you exerted the necessary force over the exact same vertical distance. You both did the exact same amount of work, and you transferred the exact same amount of energy. But I am willing to bet the crane did it a heck of a lot faster than you did. And that brings us to a really crucial distinction. That distinction is power. In physics, power strictly measures the rate at which work is done. Basically, it tells you how fast energy is being transferred from one thing to another. The formula is simply power equals work done divided by the time taken. So, looking back at our crate example, because the massive crane does the exact same amount of work in a fraction of the time, the denominator in our equation shrinks way down. And mathematically, that means the crane's power output is vastly, vastly greater than yours. We measure this rate of energy transfer in watts. Think of 1 watt as meaning exactly 1 joule of work is being done every single second. So when you screw in a standard 60-watt electric light bulb at home, that rating is literally telling you its power. It is transferring exactly 60 joules of electrical energy into light and heat energy every single second you leave it switched on. And when we're dealing with bigger things like heavy machinery or car engines, we usually use kilowatts, which is just a larger scale, 1,000 watts.
Let's bring it all home with Section 5, Energy in the Real World, High-Stakes Physics. We're going to take all these abstract formulas off the chalkboard and see how work, energy, and power dictate actual road safety laws.
A bit of history first. Before we universally adopted watts, people measured power by comparing engines to, well, horses, literally horsepower. It originally represented a single horse lifting 33,000 pounds of water 1 foot in 1 minute. Kind of quaint, right? But today, modern engineers use these exact same fundamental principles of work and energy transfer to calculate high-stakes, life-saving metrics, like exactly how long it takes a speeding 2-ton car to physically stop. Look at this data for a second. Notice what happens to emergency stopping distances as a car speeds up. When your speed goes from 8.9 meters per second to roughly double that, 17.9 meters per second, your braking distance doesn't just double, it quadruples. It rockets from 6 meters all the way to 24 meters. The total stopping distance just explodes. Why on earth does this happen? Well, it comes entirely back to the math of work and energy. This right here is the fundamental physics of road safety. When your car is moving, it has kinetic energy, which we represent as 1/2 times mass times velocity squared. To stop that car, your brakes have to do work to strip away all of that kinetic energy. So we set the car's kinetic energy perfectly equal to the work done by the brakes, which is the frictional braking force times the stopping distance. I love this quote from the text because it makes it so clear. When you slam your foot on the brake pedal in an emergency, saving your life isn't magic. It is quite literally a matter of doing work. The brake pads clamp down, applying immense friction, and over the distance the car skids, all that dangerous kinetic energy is transferred into internal thermal energy. The brakes actually get scorching hot. They are physically converting your forward movement into heat to save your life. Let's wrap this up by thinking about the math we just covered. Because kinetic energy relies on velocity times squared, if you decide to double your speed on the highway, you don't just double your forward energy, you quadruple it. And since your car's brakes can only apply a fixed maximum force, if they have to do 4 times the amount of work, you are going to need 4 times the distance to bleed off all that energy. You'll skid 4 times further before coming to a stop. Driving fast isn't just a little more dangerous, it is exponentially more dangerous because you cannot argue with the strict laws of kinetic energy and work. So the next time you're cruising on the highway, ask yourself, do you truly respect the mathematical limits of the machine you're operating? Hopefully, now you do.